Welcome to this coding walkthrough. In this video, we'll tackle problem number 1354, titled Construct Target Array with Multiple Sums. This is a fascinating problem that challenges our understanding of arrays and mathematical reasoning. Let's break it down and explore the most efficient approach to solve it. Stay tuned. The problem begins with the concept of a target array, which we are trying to construct. You are given an array, target, consisting of integers, and the task is to determine whether this array can be created by starting from an array of the same length where all elements are initialized to 1. The allowed operation is to pick any element in the array and increment it by the sum of all elements in the current array. The goal is to determine if it's possible to transform the initial array of all 1s into the given target array. The result of the problem will be a Boolean value, true if the transformation is possible, and false if it is not. To help clarify, let's look at specific examples. For the first example, the input is target equals 9, 3, 5. Starting with the initial array ARR equals 1, 1, 1, we increment elements step by step. First, we increment ARR 0 by the sum of the array, which is 3, resulting in ARR equals 4, 1, 1. Next, we increment ARR 1 by the array sum, now 6, making ARR equals 4, 7, 1. Continuing this process, we increment ARR 2 by 12, resulting in ARR equals 4, 7, 13. Finally, we increment ARR 0 by 24, which transforms the array into 28, 7, 13. By repeating this process, we successfully reach 9, 3, 5, so the output here is true. On the other hand, in the second example with target equals 1, 1, 1, 2, it is impossible to construct the target array starting from 1, 1, 1, 1. Therefore, the output is false for this case. Another example is target equals 8, 5. Starting with ARR equals 1, 1, we increment ARR 0 by the sum of the array, which is 2, resulting in ARR equals 3, 1. Next, we increment ARR 1 by the sum of the array, now 4, making ARR equals 3, 5. Finally, we increment ARR 0 by the sum of the array, which is 8, transforming the array into 8, 5. Here, the output is true because we successfully achieved the target array. These examples illustrate how the transformation process works and highlight when it is, or isn't, possible to construct the target from the initial array of all ones. The problem also imposes several constraints that must be considered. The length of the target array can range from 1 to as many as 10⁻5 elements, and each value in target can be as large as 10⁻9. This means that any solution must be efficient and scalable to handle very large inputs. There are also key edge cases to keep in mind. If the target array consists entirely of 1s, the answer is always true because no transformation is needed, the initial array of all 1s already matches the target. However, if the sum of the target array is odd, it might not always be possible to achieve the transformation. Handling large arrays or values efficiently is crucial to avoid performance issues or timeouts during computation. To solve this problem, we need to determine if it's possible to construct the target array, starting from an array of the same size where each element is initially 1. The only operation allowed is selecting any element and incrementing it by the sum of all elements in the array. A key insight here is that instead of simulating this process forward, we can reverse it. This means working backward from the given target array, reducing it step by step until we reach an array of all ones. The most critical part of this reverse process is identifying the largest element in the array at each step, as it's the one most likely to have been incremented in the forward process. By subtracting the sum of the rest of the array from this largest value, we can deduce its previous value. Throughout this process, we must also monitor for any stopping conditions, such as if an element becomes less than 1 or if the reduction cannot logically continue. If either of these occurs, we can conclude that the target array is not constructible. To approach this problem, several strategies were considered. One idea was a brute force approach, where we simulate the process of incrementing elements starting from an array of all ones, trying all possible combinations of updates to reach the target. However, this approach is computationally infeasible because the number of possibilities grows exponentially with the size of the target array. For larger inputs, this method is simply not scalable. Next, we considered a reverse simulation method that involves sorting. Here, we repeatedly identify the largest element in the array by sorting it, then reduce it by subtracting the sum of the other elements. While this method is more structured, sorting the array at every step introduces inefficiency, with a time complexity of n squared log n. Finally, the most efficient approach is an optimized reverse simulation using a max heap. Instead of sorting the array, we use a heap to efficiently track and retrieve the largest element in logarithmic time. The process involves inserting all elements of the target into a max heap, then repeatedly extracting the largest element, calculating the sum of the rest of the elements, and updating the largest element until all elements become 1 or the process becomes invalid. For the heap-based approach, if the largest element becomes 0 after reduction, we reset it to the sum of the other elements before pushing it back into the heap. This process is repeated until all elements in the array are reduced to 1, at which point we return true, indicating that the target array is constructible. The time complexity of this method is n log n, as each heap operation is logarithmic, and the structure ensures efficient retrieval and updates. This approach was chosen as the optimal strategy because it leverages the problem structure by focusing on the largest element at each step. Unlike the brute force method, it is scalable, and unlike the sorting-based approach, it avoids unnecessary overhead. In summary, the heap-based solution is efficient, systematic, and well-suited for handling the constraints of this problem. It balances computational efficiency with clarity, making it the most practical choice for solving this problem effectively. The problem requires us to determine if we can construct a given target array starting from an array of ones, where the only operation allowed is incrementing any element by the sum of all elements in the array. To tackle this, we start by validating the input. If the target array is already an array of ones, we can return true immediately since no operations are needed. However, if the total sum of the target array is less than the array's length or if any element in the target is less than 1, it's impossible to construct the array, and we return false. The key insight here is to reverse the problem. Instead of building the target array forward from ones, we simulate the reverse process, starting with the target and repeatedly undoing the operation. Specifically, we subtract the sum of the remaining elements from the largest element in the array, gradually reducing the array until all elements become 1. To efficiently handle the largest element during this reverse process, we use a max heap. In Python, since heaps are implemented as min heaps by default, we insert negative values to simulate a max heap. We initialize the heap with the negative values of all elements in the target array and calculate the total sum of the array. The reverse operation is then performed iteratively. While the largest element in the heap is greater than 1, we extract it, compute the sum of the rest of the array, and check if it's possible to reduce the largest element to a valid previous state. If the remaining sum is 0 or larger than the extracted element, we return false as it indicates an invalid state. Otherwise, we calculate the new value of the largest element using the modulo operation. If the result of the modulo operation is 0, we assign the remaining sum to prevent the value from dropping below 1. We then update the total sum and push the new value back into the heap. This process continues until all elements in the heap become 1. This approach relies on key insights to manage the problem efficiently. First, reverse engineering simplifies the process by reducing the target array to an array of ones, avoiding the complexity of forward simulation. Using a max heap allows us to efficiently access and update the largest element, which is critical for the reverse operation. The modulo operation is essential for simulating the reduction of the largest element without performing extensive iterations. Together, these techniques ensure that we handle the problem systematically and avoid unnecessary computations. The data structures used include the max heap for efficient access to the largest element and integer variables, such as total_sum, to track the sum of the array during iterations. Analyzing the complexity of this algorithm, the time complexity is determined by the operations on the heap. Each operation, which involves extracting the maximum element and inserting a new value, takes log n. The number of these operations depends on how many times the largest element can be reduced, which is proportional to the logarithm of the largest element in the target array, denoted as m. Therefore, the overall time complexity is n log m, where n is the number of elements in the target array. The space complexity is n, as the heap requires space proportional to the number of elements. Let's consider an example with target equals 9, 3, 5. Initially, the heap contains -9, -3, -5, and the total sum is 17. In the first iteration, we extract 9, calculate the remaining sum as 8, and update 9 to 1 using the modulo operation. The heap is then updated to -5, -3, -1. In the second iteration, the largest element is 5. Subtracting it from the total sum gives a remaining sum of 4. Using the modulo operation, we reduce 5 to 1 and update the heap to -3, -1, -1. In the third iteration, the largest element is now 3. The remaining sum is 2, and applying the modulo operation reduces 3 to 1. The heap is then updated to -1, -1, -1. At this point, all elements in the heap are 1, so we return true. This example demonstrates how the algorithm systematically reduces each element while maintaining the constraints. For edge cases, if the target array contains a single element equal to 1, the answer is always true. On the other hand, for cases like target equals 8, 5, the algorithm will detect invalid states where reductions are not possible, ensuring correctness in all scenarios. This implementation solves LeetCode problem number 1354, construct target array with multiple sums. The problem involves checking if a given target array can be constructed from an array of ones using a specific operation. The algorithm uses a greedy approach with a max heap. Here's the step-by-step breakdown. 1. Edge case: if the target array has only one element, it can only be constructed if the element is 1, since no operations can reduce a number. 2. Initialize variables: the total underscore sum is calculated as the sum of all elements in the target. A max heap is created by negating all elements. Python's heap implements a min heap by default. 3. Main loop: the algorithm repeatedly retrieves the largest element from the heap. The rest underscore sum is calculated as the sum of all other elements. 4. Check for valid construction. If the largest element is 1 or the sum of all other elements is 1, return true, the target can be constructed. If the largest element is smaller than or equal to the rest of the sum, or if the rest of the sum is 0, or if the largest element is a multiple of the rest of the sum, return false, impossible to reach the target. 5. Update largest element: the largest element is reduced modulo the sum of the rest of the array, largest % equals rest underscore sum. This simulates undoing the last operation applied to that element. Update the total sum and push the reduced value back into the heap. This approach ensures that the largest element is repeatedly reduced until the target array either matches the criteria or is determined to be impossible. The heap operations ensure efficiency, making the solution optimal. The time complexity is O, n log n, where n is the size of the target array, due to the heap operations. The space complexity is O, n, for the heap. To solve the problem of constructing the target array with multiple sums in Java, we begin by checking a base case. If the target array contains only one element, we can directly return whether that element is equal to 1, as a single element array can only be reduced to 1. Next, we initialize a max heap using a priority queue. This allows us to efficiently retrieve the largest element in the array at each step. Since Java's default priority queue is a min heap, we reverse the order to simulate a max heap by using a custom comparator. We also calculate the total sum of the elements in the target array, as this will help us manage the reduction process. By iterating through the target array, we add each element to the max heap and update the total sum. Now, we repeatedly extract the largest element from the heap using poll, which gives us the maximum value in the array. We calculate the sum of the remaining elements by subtracting this largest value from the total sum. These steps set up the core mechanics for checking whether the reduction process is feasible. Next, we evaluate a set of conditions to determine if the reduction process should stop. If the largest value becomes 1, or if the sum of the remaining elements equals 1, we return true because it is possible to reduce the array to the target using the given rules. However, if the largest value is less than or equal to the sum of the remaining elements, or if the sum of the remaining elements is 0, or if the largest value is not reducible further, indicated by largest % rest sum equals 0, we return false, as the configuration becomes invalid. If none of these conditions are met, the largest value is reduced by taking its remainder when divided by the sum of the rest of the elements. This simulates subtracting the sum of the smaller elements multiple times from the largest value until it fits within the valid range. We then update the total sum with the new largest value, push this reduced value back into the max heap, and continue the loop. This process ensures that we systematically reduce the array while maintaining the constraints of the problem. In this example, we start with the target array 9, 3, 5. The initial total sum of the array is calculated as 17, and we use a max heap to efficiently track the largest element. To simulate a max heap using Python's heap, we store negative values, resulting in -9, -3, -5. In the first iteration, we extract the largest element, which is 9. The remaining sum of the other elements is 8. Since the largest value is greater than the remaining sum and the remaining sum is not 0, we reduce the largest value modulo the remaining sum, giving 9% 8 equals 1. We then update the total sum to include this reduced value, resulting in 9, and push -1 back into the heap. The heap now contains -5, -3, -1. Next, in the second iteration, we extract the largest element, which is now 5. The remaining sum of the other elements is calculated as 4. Applying modulo operation, we compute 5% 4 equals 1. The total sum is updated to 5, and -1 is pushed back into the heap, resulting in -3, -1, -1. In the third iteration, the largest element is 3, and the remaining sum is 2. Performing the modulo operation gives 3% 2 equals 1. Updating the total sum to 3 and reinserting -1 into the heap leaves us with -1, -1, -1. Finally, in the fourth iteration, the largest element is 1. Since it equals 1, we can conclude that the target array can be constructed, and we return true. Now, we consider the target array 8, 5. The total sum of the array is 13, and the max heap is initialized with -8, -5. In the first iteration, we extract the largest element, 8. The remaining sum of the other elements is 5. Since the largest value is greater than the remaining sum and the remaining sum is not 0, we calculate 8% 5 equals 3. Updating the total sum to 8 and pushing -3 back into the heap results in -5, -3. Next, in the second iteration, we extract the largest element, which is 5. The remaining sum is 3, and applying modulo gives 5% 3 equals 2. The total sum is updated to 5, and -2 is pushed back into the heap, resulting in -3, -2. In the third iteration, the largest element is 3, with a remaining sum of 2. Modulo operation yields 3% 2 equals 1. The total sum becomes 3, and -1 is pushed back into the heap, giving -2, -1. Finally, in the fourth iteration, the largest element is 2, and the remaining sum is 1. Since the remaining sum equals 1, we determine that the target array can be constructed, and we return true. Finally, let's examine the target array 1, 1, 2. The total sum of the array is 4, and the max heap is initialized as -2, -1, -1. In the first iteration, the largest element is 2, and the remaining sum of the other elements is 2. Here, since the largest value is less than or equal to the remaining sum, it is impossible to reduce it further while maintaining the conditions of the problem. Therefore, we conclude that the target array cannot be constructed, and we return false. The time complexity of the solution is determined by the operations we perform on the max heap. First, we have the heapify operation, which initializes the heap structure from the input array. This operation takes n, where n is the number of elements in the target array. Then, during the main loop, we repeatedly perform heap pop and heap push operations, both of which take log n time since they maintain the heap property. The loop itself continues until the largest number in the heap is reduced to 1. In the worst-case scenario, the largest number decreases exponentially during each iteration, such as halving at each step. This results in at most log, max, target iterations, where max, target, is the largest value in the array. Together, these factors contribute to the overall time complexity of the solution. Now, combining the time complexities of the individual components, we have n for heapify and k*log n for the iterations of the loop, where k is proportional to O log max target. When we combine these, the total time complexity becomes O n plus log max target asterisk log n. For space complexity, the heap itself requires O n space to store all the elements of the target array. Additionally, we use a constant amount of space for auxiliary variables such as total_sum, largest, and rest_sum, which together take O1 space. Therefore, the total space complexity of the solution is O n, as the heap storage dominates. Let's compare this optimized approach to a naive one. In a brute force approach, we might attempt to simulate all possible sequences of operations to reduce the target array to 1. Such an approach would have exponential time complexity on the order of O2 to the power of k, where k is the number of operations. By contrast, the optimized approach uses a max heap to focus only on reducing the largest element at each step. This drastically reduces the number of operations needed, as the heap allows us to efficiently identify and process the largest element in logarithmic time. As a result, the heap-based solution is significantly faster and scales far better than the naive method. To break this down further, we can analyze the best, average, and worst-case scenarios. In the best case, the largest number in the array is already 1, or it reduces to 1 very quickly. Here, the time complexity is dominated by the heapify operation, which takes O n. In the worst case, the largest number decreases very slowly, such as when largest %rest_sum remains close to largest over multiple iterations. This leads to the full complexity of O n plus log max target asterisk log n. On average, the number of iterations is proportional to log max target, so the overall time complexity remains O n plus log max target asterisk log n. In all cases, the solution remains efficient compared to brute force methods. Finally, the mathematical reasoning behind the big O complexity highlights the efficiency of this solution. The modulo operation, largest % equals rest_sum, ensures that the value of largest decreases in each iteration. In the worst case, the decrease is exponential, resulting in O log max target iterations. Since each iteration involves heap operations that take O log n, the loop contributes O log max target asterisk log n to the total complexity. Adding the O n cost of heapify, we arrive at the final complexity of O n plus log max target asterisk log n. This proves that the solution is highly efficient, especially for large inputs, and significantly outperforms naive approaches in both time and space requirements. One of the most common mistakes in this problem is misunderstanding how the operation works. The operation doesn't just increment a single element by 1, it adds the sum of the entire array to one specific element. Misinterpreting this can lead to incorrect transformations and failed solutions. Another frequent error is assuming the problem should always be solved by building the target array starting from 1, 1, 1. While this forward approach seems intuitive, it's often inefficient. Instead, a better strategy is to reverse the process and work backward from the target array to 1, 1, 1. Additionally, edge cases can catch you off guard. For instance, when the target contains very large numbers or when all elements are the same, failing to account for these scenarios can cause infinite loops or incorrect results. Lastly, if you're working in a language like C++ or Java, be cautious about integer overflow. The sums involved in this problem can become quite large, so handling overflow properly is essential to avoid unexpected bugs. Another mistake to avoid is relying on brute force for large inputs. Simulating the process step by step without optimization can lead to time complexities that are completely impractical, especially when the target size can be as large as 10 to the power of 5. This approach simply won't scale. Now, when it comes to interviews, there are a few insights that can make a big difference. The key is recognizing that the forward approach, starting from 1, 1, 1, is less intuitive and more complicated than reversing the process. By working backward, you simplify the problem into repeatedly finding the largest element and reducing it efficiently. To optimize this, using a max heap or priority queue allows you to repeatedly access and modify the largest element in the array. This is much faster than simulating the forward process. Additionally, there's a useful mathematical observation to keep in mind. The largest element in the array at any step was formed by adding the total sum of the previous array to a smaller value. Using modulo operations here helps you reduce the largest element quickly while ensuring the solution remains feasible. When discussing this problem in an interview, it's important to clearly explain how your approach handles edge cases and constraints. For example, you should be able to articulate why your solution ensures that all elements eventually reduce to 1, or why certain target arrays are impossible to construct. This kind of clarity demonstrates a deep understanding of the problem. Additionally, this problem shares similarities with other problems you might encounter. For instance, LeetCode 1046, last stone weight, also involves using a max heap to process the largest elements repeatedly. LeetCode 2209, minimum white tiles after covering with carpets, focuses on optimizing values under given constraints, and LeetCode 502, IPO, requires efficient usage of a max heap for decision-making. Of course, the problem we're discussing, LeetCode 1354, is the central focus here, but recognizing these connections can help you see patterns in problem-solving techniques and apply them across different contexts. There are a few alternative approaches to solving this problem, each with its own trade-offs. One approach is brute force simulation. This involves starting from 1, 1, 1, and simulating the allowed operations until you construct the target array. While this method is simple to implement, it's highly inefficient for large inputs due to the exponential growth of array values. A more efficient approach is backtracking with a max heap. Here, you start from the target array and work backward by reducing the largest element using modulo operations. This method has a significantly better time complexity, around O, and asterisk log, max, target, but it does require careful handling of edge cases to ensure correctness. Finally, there's mathematical deduction. By analyzing the properties and patterns in the problem, you may be able to directly deduce whether constructing the target is feasible. While this approach is theoretically optimal, it can be challenging to generalize into a practical algorithm that handles all edge cases. Each of these approaches offers different insights, and understanding their trade-offs can help you choose the best one depending on the context. That's a wrap. In this video, we explored how to solve the construct target array with multiple sums problem efficiently using a max heap. We learned the importance of working backward and leveraging the right data structures for optimization. Thanks for tuning in, and be sure to subscribe for more problem-solving insights. Keep practicing and happy coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!